Why measure qubits in a quantum circuit? Have you ever wondered why measuring qubits in a quantum circuit is so important? Let's break it down in simple terms. Measuring qubits is essential for extracting classical information from a quantum system. And like classical bits, qubits can exist in a state called superposition. This means they can representing probabilities of being in state 0 or 1 at the same time. When we measure a qubit, it forces the qubit to choose a specific state based on its probabilities. This process is known as wavefunction collapse. Once we measure, the qubit transitions from a superposition to a definite classical state, either 0 or 1. This conversion allows us to obtain usable output from the quantum computation. Without measurement, the results of a quantum circuit would remain in a non-observable form, making them useless. Typically, measurements happen at the end of a quantum circuit to read out the final results. However, measurements can also be done in the middle of the circuit. This allows for adaptive operations based on the outcomes we get along the way. Such flexibility is important for advanced quantum algorithms and error correction techniques. Let's look at some specific roles that measurement plays in quantum circuits. First, it helps us obtain output. The measurement translates the quantum state into classical bits, which we need to interpret the results of our computations. Second, measurement collapses the qubit superposition to a definite state. This is fundamental for how quantum algorithms provide probabilistic yet meaningful answers. Third, we can use measurement for error correction. Ancilla qubits, which are extra helper qubits, can be measured to detect and correct errors without disturbing the main qubits. Fourth, measurements can also be used to entangle qubits in certain protocols. They can drive measurement-based quantum computing, where computation happens through a sequence of measurements rather than unitary gates. Finally, mid-circuit measurements allow for adaptive algorithms. This means later operations can depend on earlier measurement results, expanding the power and flexibility of quantum circuits. In practical terms, measuring qubits converts quantum information into classical bits. These bits can then be stored in classical registers for analysis or used to control further operations. Quantum programming frameworks implement this by linking each qubit to a classical bit for measurement. In summary, measuring qubits is a fundamental step that connects the quantum and classical worlds. It makes quantum computations accessible and meaningful for real-world applications.